Okay, let's go ahead and give this a shot. This is Mr. Baker, and we're going to go ahead and work through Module 9 practice problems. This is practice problem number 1. It says a chemist mixes sulfuric acid, that's H2SO4, with aluminum hydroxide. Give the balanced chemical equation that represents the resulting reaction. Now, you may not remember exactly what the formula for H2SO4, for aluminum hydroxide is, but if you remember that a hydroxide has a -1 charge, and if you look up aluminum, you'll notice that it's a column 3 element, and that means that the aluminum wants to become a +3, and the hydroxide has a -1, and so in order to have a balanced a neutral molecule, we need to have 3 of the 1 negative hydroxides to balance out the 1 3 positive aluminum. So it's H2SO4 plus AlOH3, and that's going to react to produce something. We should notice right away here that we're dealing with an acid. It leads with an H. It's also called sulfuric acid. And this must be our base, and it's an ionic base. And so we know that an acid and an ionic base reacts to produce water and a salt. And so my H2SO4 plus AlOH3 reacts to produce H2O, and now we're going to look at the molecules. We're going to lose the hydrogens from the acid, and we're going to lose the OHs from the base, and that's going to leave us with aluminum and sulfate. So it's Al, I'm going to go ahead and put it in parentheses now, SO4. The question is, how many do we need again? Now, if you remember, or even if you don't remember, let's look across here. We're going to lose 2 hydrogens, and each one has a +1 charge. So that means if we're going to lose 2 positives here, that this sulfur or sulfate here is going to have a 2 negative charge if it was balanced before. So that 2 negative. And then we know that aluminum, from our discussion before, has a 3 positive. So how do we create a molecule from those 2 different pieces of information? Well, if we know that the sulfate is a 2 negative and the aluminum is a 3 positive, we just cross the superscripts and make them subscripts. It becomes Al2SO3. So H2SO4 plus AlOH3 reacts to produce H2O plus Al2SO4 sub 3. Question is that now balanced? And it's not. So what do we do? Well, let's just count up what we have. We've got 2 hydrogens, that balances, 1 SO4, and over here we have 3 sulfates, 3 SO4s. So we know we're going to need to have at least 3 on this side. Now what does that do? That kind of messes us up here because we've got 3 H2s now. We know that that's going to, each one of those hydrogens is going to match with an OH. So we have 3 sets of H2s, or 6 hydrogens, they're going to be donated to the OHs. So if we've got the 3 H2s, we've got 3 OHs, and that's going to make 3 H2Os. We've got 3 SO4s, okay. We're going to need to have 2 aluminums to make the Al2. So we needed 2 here, but what does that do now? Well, that messes up how many hydroxides we have, don't we? We now have 6 hydroxides, so we're going to need 6 hydrogens to 6 hydroxides. Let's see, H2, it's 6. We got 3 hydroxides, so that times 2 is 6. We've got 3 sulfates, 2 aluminums, 2 aluminums. Okay, let's just do an atom count from here. We've got hydrogens. On the left side, we've got 3 sets of 2 is 2. And OHs, we're actually doing not the atom count, but a molecule count. OHs, we have 2 sets of 3. All right. And then we've got H2, oh, excuse me, H2s, OHs, we got SO4s. And we're going to have 3 of those. And aluminums. And we have 2. What do we have over here? Well, for the H2O, for hydrogens, well, there were 3 sets of 2, which equals 6. Oxygens. You see what's happened here? We have one of our hydrogens from here in the waters, but we have one of our hydrogens from here. So we've got 6 hydrogens and only 3 times 2 is 6 OHs. So it's not going to be 3 here, is it? It's 3 sets of 2, which is going to be 6. We have 6 hydrogens and we have 6 OHs to make 6 waters. So now with the 6 H2Os, we get 6 hydrogens and 6 oxygens. That matches this, matches that. Aluminum has 2, which just checks from that. Sulfate has 3, checks from that, and that's our balanced equation. 3 H2SO4 plus 2 aluminum hydroxide reacts to produce 6 H2O and Al2SO4 sub 3. Okay, number 2. This was number 1, number 2. It says, give the balanced chemical equation for the reaction that occurs between nitric acid, that's HNO3, starts with an H, it's named nitric acid, so it's probably the acid, and calcium hydroxide, CaOH. Now, calcium, where does calcium sit on the periodic table? Calcium is a column 2 element, so it wants to go 2 positive, and each hydroxide has a 1 negative, so there's going to be 2 of those. CaOH 2. So nitric acid and calcium hydroxide, we're balancing the equation between the reaction. So again, we have an acid and an ionic base, which is going to produce water and a salt. So we know we're going to make water, and we know we're going to make a salt, and the salt is going to lead with the metal from the base, and it's going to end with the remainder after we remove the hydrogen from the acid. So it's an NO3 molecule. The question is, how many? Well, the molecule has a charge of -1, and we know calcium has a charge of +2, and so we're going to need 2 of those to balance out the charges in the molecule. So let's go through now and look at, we're going to have 1 hydrogen and 2 hydroxides. Well, each hydroxide is going to need 1 hydrogen to bond with to form water, so we're going to have to start with 2 at least, and that's going to give us 2 waters. So 2 hydrogens plus 2 hydroxides produces 2 waters. Then we're left with the remainder. We've got 1 calcium, and we've got 2, and it checks. And so, after balancing it, it is 2 HNO3 plus CaOH2 reacts to produce 2 H2O and CaNO3 2. And number 3. Given that ammonia, that's NH3, is a base, assuming I'm going to be given an acid to react it with. Determine the reaction that occurs between H2CO3, H2CO3, and ammonia, and give the balanced chemical equation. Reacts to produce what? Now, it's a little bit different than the first two. The first two we had acids and an ionic base. This time we have an acid and a covalent base. So remember we said we're going to take one hydrogen and match it up with each of the bases. So a hydrogen is going to be added to the base, which is going to react to produce NH, add one hydrogen, NH4. So from ammonia, we're going to produce ammonium, so NH4. Well, what else is left after that? We have NH4, and so NH4 takes one of these. We've got two of them, right? So we need at least two here, which is going to produce two. And then the remaining ion. The ions are going to be left behind. The only thing that's not consumed is right here, a CO3 plus CO3. And if you look at this, we're losing the two positive hydrogens. It's going to have a 2 negative charge. And so H2CO3 plus 2 NH3 reacts to produce 2 NH4, and that's going to be a positive 1, plus CO3, and that ion has a negative 2 charge. Number 4 says when HBr, bromic acid, HBr, is mixed with water, what chemical reaction occurs? And give the balanced chemical equation. So we've got water and an acid. So what are they expecting you to remember here? Well, you'd assume that we're talking about acids and bases, right? Normally, we talk about water being a product, but we also learned something unique about water in that water is amphiprotic or amphoteric. And that means that water can act as both an acid or a base as needed in the equation. So looking at this equation, we have an acid, hydrobromic acid, or bromic acid, yep, HBr, and water. So we have an acid and a base. And what kind of a base is it? Is it ionic or is it covalent? It's a covalent base. So how does an acid and a covalent base react? The acid's going to donate a hydrogen to the base, and then the remainder is going to be left as an ion. So if we add one hydrogen per water molecule, the covalent base, we get an H3O, or hydronium, heavy water, positive, plus a bromide, a bromine ion, 1 negative. And that's the answer to number 4. Number 5. Give the concentration in molarity for each of the following solutions. A. 3.5 moles of HNO3 are dissolved in enough water to make 1.2 liters of solution. So how are we going to do that? Well, the concentration, remember, just abbreviate C-O-N-C. Concentration, this is our molarity. Molarity is equal to the number of moles divided by the volume. So moles divided by volume. In this case, the number of moles is 3.51 divided by the volume, and the volume being 1.2 liters. So it's 3.51 moles divided by 1.2 liters. And the answer is 2.9 molarity. That's 2.9 moles per liter. B, second part. we have 234.1 grams are dissolved in enough water to make 345 milliliters of solution. Well, the first step here is we've given potassium hydroxide in grams, and we can't determine the molarity using grams, so we're going to have to convert from grams to moles. The molar mass of potassium hydroxide is 39.1 AMUs for the potassium and 16 AMUs for the oxygen and 101 AMUs per hydrogen, means it's 56.1 AMU. Also turns out to be 56.1 grams per mole. So here for the number of moles, we're going to have 234.1 grams divided by 56.1 grams per mole. And that's going to give us 4.17. Yeah, that makes more sense. 4.17 moles of potassium hydroxide. We've already been given the volume of 345 milliliters, and so our molarity here is equal to 4.17 moles for every 0.345 liters. Take 345 milliliters and convert it to liters. So we go 1, 2, 3, move the decimal place 3 places to the left, add a leading 0, 0.345 liters. And so the molarity then is equal to 12.1 molarity, 12.1 moles per liter. And the final part, C. C says you're given 4.1 grams of H3PO4, and they're dissolved in enough water to make 45 milliliters of solution. Well, just like before, we're going to have to take the mass, 4.1 grams, and divide that by the molar mass. The molar mass of the molecule is 98 AMU, which means it's 98.0 grams per mole. And when we do that math of 4.1 divided by 98.0, it's going to give us 0.042 moles. So we've got 0.042 moles of H3PO4. Then that's dissolved in enough water to make 45 milliliters. Same thing as before. We've got the moles now, 0.042 moles for every 45 milliliters is rewritten as 0.045 liters. Take the decimal, 1, 2, we move it to the third spot. We need a 0 to hold that place. Put a leading 0 and change it to liters. So 0.045 liters. 0.042 moles in 0.045 liters is going to produce something really close to 1 molarity. The math actually turns out to be 0.93 molarity, or 0.93 moles per liter. And let's go ahead and finish with number 6 for the sheet. Number 6. It says a chemist has 12 molar hydrobromic acid and would like to use it to make 500 milliliters of 3.5 molar HBr. Describe how she would do this. Okay. So we've got a 12 molar acid, and we want to make 500 milliliters of a 3.5 molar acid. So we're going to be diluting it. Of course, the dilution equation. The molarity to start and the volume to start is equal to the molarity at end and the volume at end. In this case, we have a molarity to start of 12.0 molar, and we have an unknown volume of that which we're going to use to make the end state. That product has to equal the molarity of the end state, which is 3.5 molar times 500. Now, I wrote that in milliliters. If I'd used liters, it'll work as long as I remember my answers in liters. If it's easier for you to just change that to 0.500 liters, that's fine. Then your first volume is going to be in liters. In this case, I used it as 500 milliliters, and I have to remember that my answer is going to be in milliliters. So we rearrange for this. The first volume is equal to 3.5 times 500 divided by 12.0. And that math works out to be 1.5 times 10 to the second milliliters, or 150 milliliters. This is the correct answer, but this is another way of writing that. 150 milliliters. So what's the chemist going to do when we describe what she does? She measures out 150 milliliters of a 12 molar solution. She then adds that amount of solution into another container and adds water to that container until she has a total solution volume of 500 milliliters, or 1/2 of a liter. And when she's done, she will have 1/2 liter of a 3.5 molar bromic acid, hydrobromic acid. Number 7. A chemist makes a stock solution of sodium hydroxide by dissolving 950 grams of sodium hydroxide in enough water to make 2 liters of solution. If later on he wants to use his stock solution to make 100 milliliters of 0.1 molar sodium hydroxide, how would he do it? Well, the first step is in addition to the last problem. We're going to eventually get to the M1V1 equals M2V2, but before we do that, we have to figure out the initial molarity. Now, if we had been given moles, we would just take the moles divided by the volume and have the molarity, moles per liter. But we don't have that in this case. We've been given 950 grams. So the first thing we have to do is figure out how many moles of sodium hydroxide we have when we actually have 950 grams. The molar mass of sodium hydroxide is 40 AMU. So, knowing that I have 950 grams of sodium hydroxide, and I divide that by the molar mass of we're going to divide that by the molar mass of 40 grams per mole, I find out that when I have 950 grams, another way I can say that is that I have 23.8 moles of sodium hydroxide. Now that I know how many moles of sodium hydroxide I have, I can figure out the molarity of my solution, because molarity is equal to moles, which in this case is 23.8 moles, divided by the volume. I've got 23.8 moles in 2 liters, and so the molarity comes out to be, or the concentration, another way of saying that, comes out to be 11.9 molarity. So my starting solution, my base solution, my M1 is equal to 11.9 molarity. Now we see that we have a dilution equation because we've got a beginning amount, or beginning molarity, and an end volume and an end molarity. The question is, if we want to take this initial and make the final, how much of this initial do we need to make the final? So we know that M1V1 is 11.9 molarity, that's my M1, and my initial volume is going to be equal to my M2, which is going to be 0.10 molar, times my V2, the volume, and if I just go ahead and use 100 milliliters, now I know that my answer, my V1 over here, is going to be in milliliters as well. Solving for V1, that V1 comes out to be 0.84 milliliters. So what does that mean? Well, what this chemist is going to do is take his 11.9 molar solution and measure out 0.84 milliliters of it. He's going to take that 0.84 milliliters and put it into a container and fill that container until he has 100 milliliters total. And when he has 100 milliliters total, he will then have a 0.10 molar sodium hydroxide mixture. And we're taking something very concentrated, putting it into another container and adding water to it to dilute it to get to the second concentration. It's number 7. Number 8, a chemist reacts 50 milliliters, so we have 50 milliliters of a 4.5 molar carbonic acid with excess potassium hydroxide. How many grams of potassium carbonate are produced? Right, here we go. Let's just look at the general reaction formula. H2CO3, that's our carbonic acid, is reacted with excess, whatever I'm about to write, I've got plenty of it, with excess potassium hydroxide, KOH. How many grams of potassium carbonate are produced? Well, we know we're going to have potassium carbonate as a product of reaction, right? We have an ionic base, and we have an acid. It's going to react to produce water and a salt. So the hydrogens and the hydrogens here, we can see that we've got 2 hydrogens. We need 2 OHs to make water. So 2 hydrogens and 2 OHs form 2 waters. And then we're going to have 2 potassiums and 1 carbonate, which will work because we're losing 2 positives. The carbonate has a 2 negative charge. The 2 negatives are going to be balanced off by the 2 1 positives of the 2 potassiums. And so it's going to be K2CO3. All right, so now we have a reaction equation and it's balanced. Now what we're doing is going to be stoichiometry. We know that we have 50 milliliters of a 4.5 molar. All the question is really asking us is, given so many moles of acid, how many moles of the salt is going to be produced? Now we don't know how many moles we have directly, but we can compute that indirectly. We've got milliliters and we've got molarity. Right, 4.5, yes. So, one way you could think about this is we have 4.5 moles for every 1 liter, but we actually have only 0.050 liters. That's another way of writing 50 milliliters. Move the decimal 3 to the left. 1, 2, 3. You got a 0 to place hold. 0.050. 0.050 liters is 50 milliliters. And we know that the molarity times the volume is going to produce the number of moles. And so here we have 0.23 moles of acid. Well, if we've got 0.23 moles of acid, how many, what are we looking for again? Potassium carbonate. There's our potassium carbonate. If we have 2 moles, or 0.23 moles of the acid, how many moles of potassium carbonate are produced? Well, using stoichiometry, look at the coefficients. For every one that we start with, how many do we produce? We produce 1. And so it's a 1-to-1 relationship, meaning for every mole of acid, we produce 1 mole of potassium carbonate, and we know that we're going to use it all because we have excess potassium hydroxide. So it's a 1-to-1, which means that we're going to produce 0.23 moles of potassium carbonate. This was moles of carbonic acid. So 0.23 moles of potassium carbonate are produced. It doesn't ask us for moles though, does it? So if you're using your solution diagram, weren't given moles, you were giving volume and molarity, so you did the multiplication to come up with moles. You used pure stoichiometry to calculate, based on the mole ratios, how many moles you would have, and now it's asking us for our answer in grams, which means we need to convert from moles to grams of potassium carbonate. The moles of potassium carbonate times the molar mass, right? Because moles, and we're going to get grams per mole, equals grams. We got 0.23 moles of potassium carbonate, and the molar mass is 138.2 grams per mole. So when we do the math, we're going to end up with grams, and the grams comes out to be 32. 32 grams of potassium carbonate. So again, we went to moles of acid indirectly by taking the molarity times the volume, and that gave us moles. We use stoichiometry to relate how many moles of acid to how many moles of base, and we see it's a 1-to-1. Since I have 0.23 moles of acid, I must produce 0.23 moles of my potassium carbonate. If I've got 0.23 moles of potassium carbonate, and each mole has a mass of 138.2 grams per mole, that means that I have produced 32 grams of potassium carbonate. Number 9. See, number 9 says, a chemist needs to know the concentration of some sodium hydroxide that is in the laboratory. To find this out, she titrates a 50 milliliter sample of the solution with 3.5 molar hydrochloric acid. If it takes 34.3 milliliters of hydrochloric acid to reach the titration endpoint, what is the concentration of the sodium hydroxide solution? Well, let's just first of all start by looking at the reaction formula. Okay? The reaction formula for this one, we've got a certain concentration of sodium hydroxide, and she's going to titrate that with hydrochloric acid. Just by convention, I'll put the acid first. That's going to be my base. Hopefully you recognize that hydrochloric acid is an acid because it starts with a hydrogen. It's also hydrochloric acid. We know that sodium hydroxide is a base because hydroxide is our most common base. An acid and a base, this is also an ionic base, means it's going to produce water and a salt. We've got a hydrogen and a hydroxide that makes H2O, and we have the metal from our base and the remainder from our acid, and we're going to produce sodium chloride. So we're salt and water, making salt water from hydrochloric acid and sodium hydroxide. So is it balanced? Well, 1 and 1 hydroxide makes 1 water, and 1 sodium and 1 chloride makes sodium chloride. So we're good. That is our balanced reaction. Pretty straightforward. It's a 1 and a 1 produces 1 and 1. So the stoichiometry part is going to be pretty simple. You must be focusing on conversions between moles and moles. So let's look at the problem again. To find this out, she titrates 50 milliliters she's titrating 50 milliliters of the sodium hydroxide, of the sample of which is the sodium hydroxide. She titrates 50 milliliters of of the solution with a 3.5 molar hydrochloric acid, if it takes 34.3 milliliters to reach the titration endpoint, what is the concentration of the sodium hydroxide? Okay. Basically what we're looking at here is when this acid is titrated against this base and we reach the endpoint, what's another way of saying that? That we have added exactly the right number of moles of acid to equalize the right number of moles of base. And if you look at it, this is a 1-to-1 relationship. So we need just as many moles of acid as moles of base to reach the titration endpoint, to reach that point of neutralization. So let's take a look at this. Let's figure out how many moles of hydrochloric acid we've actually used. How many moles? Well, the moles, remember, molarity is moles per liter, 3.5 moles per liter. And if I multiply that by the volume, I'm going to put this in liters so I can keep my units straight, 0.0343 liters. If I were to go ahead and do that math, I'm going to go see that we'd used 0.12 moles of hydrochloric acid. And because I used 0.12 moles of hydrochloric acid, based on this balanced reaction equation, that means I must have balanced it against 0.12 moles of sodium hydroxide, because it's a 1-to-1 relationship. If I had 0.12, it must have reached the endpoint when I had 0.12 moles of my base. Well, I have 0.12 moles of my base when I've added 0.050 liters of my solution. So remember, concentration is moles per liter, or in this case, I was able to determine I used up 0.12 moles of my base when I added 0.050 liters of my solution. And that gives me a 2.4 molarity. The base, the sodium hydroxide, is at a 2.5 molar concentration. Again, because this is a 1-to-1, see the stoichiometric coefficients? Implied 1, implied 1. It's a 1-to-1. What does that mean? For every mole of acid, I need a mole of base. When I hit the end point, that means I'm perfectly balanced. I had a 3.5 molar acid, and I used 34.3 milliliters of that, which meant that I used 0.12 moles of my acid. If I used 0.12 moles of the acid, it must have balanced against 0.12 moles of the base. Because I had 0.12 moles of the base, when I added 50 milliliters of the base, that means the concentration was 2.5 molar. And number 10. A solution of H2SO4 is titrated against potassium hydroxide, and it's a 1.2 molar potassium hydroxide. A total of 345.1 milliliters of potassium hydroxide must be added to a 500 milliliter sample of the acid to reach the endpoint. What is the concentration of the acid? Okay, so like always, we have to start with a balanced reaction equation. We've got an acid and a base that reacts to produce. Now this is an ionic base. It's got hydroxide in it, potassium hydroxide. This is a polyprotic acid. It's actually a diprotic, so it's going to give 2 hydrogens. And so for every hydrogen, we need an OH for it to react with, so we're going to end up needing 2. Why? 2 hydrogens require 2 OHs. We can get that by putting the 2 in front of it. But I probably got a little bit too quick there. Let me go back and let's stop and look at what are we going to produce. We're going to produce water and a salt. The salt is going to be the metal from the base and the ion from the acid, potassium sulfate. So, this has a -2 charge, which means we need 2 positives to balance it off. Potassium is a column 1 metal, so we're going to need 2 of those to balance off the charge of the sulfate to make that a neutral molecule. So it's K2SO4, H2O. Let's look at it. I already know I need 2 OHs, so I put that in advance. Let's look at it now. We got 2 hydrogens and 2 OHs to form 2 waters. And we've got 2 potassiums and 1 SO4. 1 potassium and 1 SO4 that react to produce 2 potassium SO4. Okay, so we're balanced. Okay. So the question then is, we're titrating these 2 against each other. We've reached the end point. What does that mean? That means the appropriate number of acid, appropriate number of moles of acid has balanced with the appropriate number of moles of base. Okay. And what do we know? Well, we know over here the molarity and the volume of our base. Let's figure out how many moles of base we actually used in titration. Molarity, remember, is moles per liter times the volume. Molarity times volume is going to give us our number of moles. In this case, we used 0.3451 liters. And that is going to produce, or that math comes out to be 0.41 moles of potassium hydroxide. So when we use 1.2 moles, when we use 345.1 milliliters of a 1.2 molar potassium hydroxide, we have in effect used 0.41 moles of potassium hydroxide. Now, my stoichiometry, I'm trying to figure out how much acid, right? If this is 0.41 moles, and I have a 1 to 2, going in this direction, my multiple is going to be times 1/2. From 0.41, then this is going to be 0.205. I'm going to round this up to 0.21 moles. So when we use 0.41 moles of base, we have to titrate that against, or balance that against, 0.21 moles of the acid. How do I get 0.21 moles? Well, my molarity times my volume equals moles, right? If I need to determine the molarity here, I can do that by saying the molarity is equal to the number of moles divided by the volume. The number of moles is 0.21 moles. The volume I used was half a liter, 0.500 liters. So I'm dividing that in half, and I end up with a molarity of 0.42 molarity. Now don't let this confuse you. Well, we're not saying that we used 0.42 moles. We used 0.21 moles. But we're in a solution that has a 0.42 molarity. We used half of a, if we compare those, we used half of a milliliter. Or excuse me, half of a liter. We used 500 milliliters. So the fact that this is 0.42 and 0.41, that's coincidence. Don't worry about that. What we're seeing here is, okay, we used this many moles of potassium hydroxide. For every mole of potassium hydroxide, it reacted against a half a mole of acid, or half as many. That half as many comes from its molarity times its volume. So the molarity is the moles per volume, which we know we used 0.21 moles when we used 500 milliliters, and that means we have a 0.42 molarity, or 0.42 moles for every liter of our acid.